Hello guys, welcome back to my channel and rise and shine for another nice video. So now, in the previous video we dealt with one of the problems from the Open Mathematical Olympiad of the Belarusian Russian University, and I believe that that problem that we solved in the last video came in 2018, and now in this video let's specially solve a problem that came in 2014. Okay, so like always, let's get started. Okay, so the problem at hand is called I, and is defined as integral from 0 to infinity of x squared minus 4 over x squared plus 4 times sine of 2x divided by x dx. Okay, and looking at the denominator, forget the numerator for now, just look at the denominator. There is a product of this quadratic term and this linear x term. So noticing that pattern, we can actually try to perform some partial fraction decomposition on the denominator, and then after performing partial fraction decomposition we'll just uh, I don't know, just put the numerator on top of uh, the different partial fractions. So just look at the fractions. So x squared minus 4 over x squared plus 4 times x. For partial fraction decomposition we only look at the polynomial terms that we have. So just ignore sine 2x, take everything else. We'll just put the sine 2x on top of all the partial fractions. So this can be expressed as ax plus b divided by x squared plus 4 plus c divided by x. Okay, and if we do a cross multiplication, the denominators will cancel out, giving us x squared minus 4 is equal to ax plus b multiplied with x plus c times x squared plus 4. And now just taking the x squared terms common, if a plus c plus bx plus 4c and x squared minus 4 on the left hand side. So now comparing coefficients, we know a plus c should equal 1 and b will therefore be 0 because there is no x term, and negative 4 will equal 4c, which means c is equal to negative 1. So a minus 1 is equal to 1 and a is equal to 2. Fair enough. A is 2, b is 0 and c is negative 1. So now this fraction that we started with now just becomes 2x divided by x squared plus 4 minus 1 over x. Fair enough. Now we're going to actually put the sine 2x on all of these things. So our integral now becomes integral from 0 to infinity of 2x over x squared plus 4 minus 1 over x, and this is multiplied with the sine 2x that we promised to put in later. That's our integral. Okay, now we can just split this up into two parts. Integral from 0 to infinity of 2x over x squared plus 4 times the sine of 2x dx minus integral from 0 to infinity of sine 2x over x dx. Okay, fair enough. Now we can actually call this I1 and call this I2, but the thing is I2 looks awfully familiar. This is just the Dirichlet integral. And one special thing about the Dirichlet integral is no matter what constant you have inside, multiplied inside the argument of the sign, whatever is multiplied with x, it can be 2, 4, anything, any real number. This Dirichlet integral I2 will always be pi over 2. And I have actually made, I think, 2 videos on this, if I'm not wrong, to actually explore this idea that no matter what constant you have multiplied with the x in the argument of the sign, the answer will still be pi over 2. So our problem I is actually equal to I1 minus pi over 2. And that's our general equation that we need to work with. And in order to actually evaluate this, we need to find I1. So let's do that on a fresh page. See you there. As promised earlier, we have our I1 being equal to integral from 0 to infinity of 2x over x squared plus 4 multiplied with sine of 2x dx. And now what I'm going to do is, noticing the upper and lower bounds are going from 0 to infinity, this actually means that I can use the Laplace transform trick. So what I'm going to do is I'm going to take the Laplace transform of sine 2x and therefore the inverse Laplace transform of this other expression, which is 2x divided by x squared plus 4 dx. So we can pull the 2 outside. 2 times integral from 0 to infinity of the Laplace transform of sine of 2x times the inverse Laplace transform of x over x squared plus 4 dx. Okay. And then, well, the Laplace transform of the sine of 2x is quite easy to calculate. It's 2 over x squared plus 4, and the inverse Laplace of this is again easy. It's cosine of 2x dx. So take the 4 outside, integral from 0 to infinity, cosine of 2x divided by x squared plus 4 dx. Okay, now what I can do is, notice that cosine is even. X squared plus 4, a quadratic term, will always be even. So then, using symmetry, I can say that integral from 0 to infinity is just half of integral from negative infinity to infinity of cosine of 2x divided by x squared plus 4 dx. Just using symmetry here and noticing that the cosine and x squared plus 4 are even functions. Just this thing, nothing extraordinary here. So this becomes 2 times integral from negative infinity to infinity of cosine of 2x divided by x squared plus 4 dx. And you know what the great part about this, using the Laplace transform was that we got rid of the x that was in the numerator. So all our polynomial terms are in the denominator, and all our trigonometric terms are in the numerator. And another great thing of using symmetry was we got our integral from minus infinity to infinity. And if you have like good intuition, you may notice that these bounds from negative infinity to positive infinity are excellent for using complex analysis or contour integration. Okay, so with our I1 looking like this, to use actually contour integration or complex analysis, we need to define a complex function. Duh. So let's call that f of z. F of z we can define as e to the 2iz divided by z squared plus 4, where z is actually a complex number. where z is a complex number defined by x plus iy, by just notational convention. Now we have our complex function. How is our contour going to look like exactly? So for that, this is actually how our contour is going to look like. It's going to be this semicircular thing, and call this the real axis, imaginary axis, this 0. This point over here, call it r. This point over here, call it negative r. So what we are going to do, the way we are going to do this is, we are going from negative r to 0, then from 0 to positive r, and then from r we're going to loop back to negative r in this semicircular way. And I'm going to call this semicircular path as beta. Okay, so the way we're going to do this is, the contour integral or the closed integral on this entire loop of f of z dz is equal to integral from negative r to r of f of z dz plus integral over beta of f of z dz. But notice that from on the path of minus r to r, we are completely on the real axis. So the imaginary component or the y coefficient will always be 0. The coefficient of I will always be 0 because we are on the real axis. So just for path 1, or the path from minus r to r, z is equal to x, nowhere else. So we can make that change over here. So we have integral from minus r to r of f of x dx plus integral over beta of f of z dz. Just substituting for f of x now, we have integral from minus r to r of e to the 2ix over x squared plus 4 dx plus integral over beta of f of z dz. Okay, and in case you were wondering, instead of this cosine 2x, why did we take e to the 2iz? That's because we are actually trying to generalize. When we do complex analysis, we actually try to generalize stuff. So e to the 2iz by Euler's formula is cosine of 2z plus I times sine of 2z. And whenever you have a cosine or a sine term, always use exponentials of this form. That's actually the right way of doing it, nothing else. So what we're going to do is actually look at this integral over beta, because we can actually make that disappear. So see you on a fresh page where I'll be doing the estimation lemma for beta. Okay, so welcome to the page that's officially dedicated to integral over beta of f of z dz, but not actually the integral over beta, but more like the modulus of the integral over beta, and that is less than or equal to integral over beta of the modulus of f of z multiplied with the modulus of dz. So now let's just plug f of z in here. So if integral over beta mod of e to the 2iz divided by z squared plus 4 times mod dz. Okay, and we can actually represent that as, we can split the mod over the fraction. So mod of e to the 2iz divided by mod of z squared plus 4 mod dz. Now we actually need to parameterize everything, because our beta was actually this semicircular path like this. So we can make a parameterization. Say let z equal to the radius r times e to the I times t. Okay, and when we do that, then we have our bounds from 0 to pi because of the angle it subtends of 180 degrees. Then mod of e to the 2i r times e to the it divided by z squared is just r squared e to the 2it plus 4, and we need to calculate dz. Dz is ri e to the it. So mod of dt ri e to the it dt. Now one nice simplification we can actually do is that, there is this inequality that basically says that if you have a mod of z squared plus a, that's always greater than or equal to mod of z whole thing squared minus a. So when we take the reciprocal, we have 1 over mod of z squared plus a is less than 1 over mod of z the whole thing squared minus a, and we have exactly the same thing here. So this is less than or equal to integral from 0 to pi of, well, e to the anything, treat the 2r e to the it as a separate angle. The mod of e to the I times some angle will always be 1 divided by, now we can write our denominator in terms of this inequality over here, giving us mod of r times e to the it the whole thing squared minus 4, and then we have mod of r I e to the it dt, and that just becomes, well, mod of r will be just r because that's just the radius of the path. Mod of I is 1, mod of e to the it will still be 1, mod of dt is dt, divided by mod of r is r, e to the it will become 1. So we have r squared minus 4 like that. And now at this point, I would like to take the limit as r goes to infinity. So as r goes to infinity, the denominator will naturally dominate, being of order 2. So this entire thing will just become 0. So you know what that means? That means that the mod of integral over beta of f of z dz is less than or equal to 0, following this trail of less than or equal to's. But we know that the mod is either 0 or greater than 0. It can never be negative. So this mod of mod of the integral of f of z dz is actually trapped between these two inequalities, and in order to satisfy both of them, it has to be equal to 0. So this will become 0. So our integral over this semicircular path will become 0. Okay, so that means this will become 0. So for our contour integral, we just need to now use the residue theorem because the other difficulties just went away. So to calculate this separately, we need to use the residue theorem. So let's do that on a fresh page. Okay, in order to find the residues of f of z, we actually need to find those points of singularities or poles. Basically points where the denominator becomes 0, making the entire f of z undefined. So for that, we can factorize the denominator as z plus 2i multiplied with z minus 2i, just the glorified difference of squares identity. That's f of z. So there are 2 points where the denominator will be 0, 2i and negative 2i, but we need to be worried about those points that lie inside our contour. So 2i is somewhere over here, negative 2i is somewhere over here. So negative 2i does not lie inside the contour, so forget that. All we need to worry about is this residue at 2i. So the residue at z equals 2i of f of z is actually given by uh, z minus 2i. First limit as z goes to 2i, z minus 2i times f of z. So when we do that, we have limit as z goes to 2i of z minus 2i times e to the 2iz divided by z plus 2i, z minus 2i. Stuff cancels out. Now we can actually plug this in. So we'll have e to the 4i squared divided by 2i plus 2i is 4i. I squared is negative 1. So e to the negative 4 over 4i. But how is this residue actually useful? That's because of the residue theorem, which says the contour integral of this contour, which actually contained this residue point, this pole at which using which we calculated the residue. Contour integral over that region is always equal to 2 pi I times the sum of residues inside that region. Since we only have one uh, singularity we need to worry about, and that's why we got one residue. Sum of residue is just that, equal to that point. So e to the negative 4 divided by 4i. The i's will cancel out. So we have pi over 2 times e to the negative 4. Fair enough. That's actually the value of the contour integral f of z dz. Now let's go back to our original page where we drew the contour. Okay, so we know that this contour integral is pi over 2 times e to the negative 4. Okay, so pi over 2 times e to the negative 4 is equal to this. And we can again take the limit as r goes to infinity, because we took the limit as r goes to infinity for this estimation lemma case. So, evaluating at the limits, we have integral from minus infinity to infinity of e to the 2ix over x squared plus 4 dx, and which we can expand, by the way, in terms of cosine of 2x divided by x squared plus 4 dx plus I times integral from negative infinity to infinity of sine 2x divided by x squared plus 4 dx. All I've done is use Euler's formula. E to the ix is cosine x plus I times sine of x. We have pi over 2 times e to the negative 4. So notice that we have a real value on the left hand side. So that means this imaginary part has to equal 0, comparing coefficients. So this will have to be 0. That means the real part, which is the cosine part, is equal to this. And this is just half of I2, right? I2 is 2 times this. So this is, I1. I1 over 2, which is equal to pi over 2 times e to the negative 4. The 2's will cancel, which means I1 is equal to pi times e to the negative 4, which you can write as pi over e to the 4. Okay, so to end with everything, we know the grand equation I is equal to, I1 minus pi over 2. I1 turned out to be pi times e to the negative 4 minus pi over 2. It seems we can take the pi out common. We have 1 over e to the 4 minus 1 half, which has an approximate value of negative 1.51326. And this is in turn equal to integral from 0 to infinity of x squared minus 4 over x squared plus 4 sine of 2x divided by x dx. So there we have it. We solved the problem from the Open Mathematical Olympiad, the problem from 2014. So that's it for this video, guys. Hope you liked it. So yeah, before going, I would like to tell you, please like, share and subscribe to my channel. I want to hit 100 subs. Please recommend me to your friends, and keep doing math. Stay home, stay safe, peace out, and please stay tuned for future videos. There's going to be a lot of new exciting content to explore. So yeah, peace out.